Let's look at an example of Newton's universal law of gravitation. Specifically, we're going to be focusing on relative forces, forces between objects relative to other forces between objects. But first, let's review Newton's universal law of gravitation. That is, an attractive force F is equal to a constant G multiplied by the masses of each objects m1 and m2 and divided by the separation distance between m1 and m2 squared. So basically we have some object m1 that is separated from the center of one object to the center of the other object by a separation distance r, and the other object has a mass 2. Our universal gravitational constant G is 6.67 times 10 to the minus 11th Newton meter squared, and notice it says kilogram to the minus 2. What that means is Newton meter squared divided by kilogram squared. So now let's look at what we're given. We're given in our example the mass of Io is 8.93 times 10 to the 22 kilograms. The mass of Europa is 4.80 times 10 to the 22 kilograms. The radius of Io to its host planet is 0.002819 AU, and the radius of Europa to its host planet is 0.004485 AU. And R is not, it's a separation distance. The goal here is to find the gravitational force of Io to Jupiter relative to that of the gravitational force of Europa to Jupiter. In other words, we want to find the force of Io to Jupiter divided by the force of Europa to Jupiter. We want to express our numeric answer with no units and to 2 decimal places. So it's either 12, for example, 12, 1.2, 0.12, or 0.012. Notice we only include the zeros to the right in the number of decimal places. There's no zeros to the right of 0.012. So there's only 2 decimal places, 1, 2. Therefore, there's only 2 decimal places there. So let's start off with our equation. We know we want to find the force of Io to Jupiter divided by the force of Europa to Jupiter. So that's going to equal, we have to put GMM over R squared on both the top and the bottom. So I have a big division symbol, and we have GMM over R squared on the top and GMM over R squared on the bottom. On the top, we're looking at Io's mass to Jupiter's mass and the separation distance of Io to Jupiter. And on the bottom, we're looking at Europa's mass to Jupiter's mass and the separation distance of Europa to Jupiter. Now we need to eliminate like variables. And as we already noticed, G is common, so we eliminate G. And the mass of Jupiter is common in both the top and the bottom, and therefore we eliminate them. What's left is the mass of Io divided by the mass of Europa. Let's start with that. So we carry that down. The mass of Io divided by the mass of Europa. The radius of Io squared is in the denominator, so we put the radius of Io in the denominator, and the radius of Europa kicks to the top. So we have the radius of Europa, and both of these are squared. Now we're just going to substitute in some values. The mass of Io is 8.93 times 10 to the 22 kilograms, divided by the mass of Europa, 4.80 times 10 to the 22 kilograms. And then we want to multiply that 0.00485 AU, the separation distance of Europa to Jupiter, and divide that by 0.002819 AU, which is the separation distance of Io to Jupiter, squared. Now we need to multiply this out. So we need to go to the internet and get our scientific calculator. So you would go to Google and type in scientific calculator or calculator, and up would pop up this Google calculator. So the first thing I want to do is type in 0.00485 divided by 0.002819. So here's our Google calculator. We're going to type in 0.0048, and I need to get the other one out. So it's 0.00485 divided by 0.002819. 485 divided by 0.002819. Let me confirm it. 2819, that is correct. So now we want to hit equal. Now notice the next thing we need to do is just square it. So let's go ahead and square it. So we're going to hit the X to the Y key with a square and hit equals. Now we've got the squared value. Next thing we want to do is multiply by 8.93 times 10 to the 22. So we're going to hit the multiply symbol, 8.93 EE22. I'm going to go ahead and hit that. And we know we have to divide by next. So let's go take a look at what we need to divide by. 4.80 times 10 to the 22. So we type in 4.80 EE22 and we hit equals, and we have a value of about 5.51 because we have to round up. The 68 is above 50, so that kicks this 0 over to 1, so we have a 5.51 as our final result. So we carry that down, and we have 5.51. So we have three values here, 3 significant digits here, 3 here, and 4 there. So 3 is the appropriate one because it's the smallest number, and we're just going to carry it down. It's the force of Io divided by the force of Jupiter. So we know that the gravitational force of Io is much more than the gravitational force that Europa feels towards Jupiter. And that's understandable because Io is the closest moon to Jupiter, and Europa is further out. So let's take a look at a little diagram of this system. So if Jupiter is in the center, and of course this is not going to be drawn to scale, but we can put Io as its orbit. So we'll put a little moon here and call it Io. And then further out is another Galilean moon orbiting around Jupiter, and that one is Europa. So Europa is much further away than Io is, and since distance matters more than mass, it makes sense that the gravitational force between Io and Jupiter is much more than the gravitational force between Europa and Jupiter. And in fact, it's 5.5 times more. And that is our final result.